Controlled environment plant production engineering technology education modules are developed and presented in collaboration by The Ohio State University, Rutgers University, and the University of Arizona, with support from USDA, NEFA, through their Higher Education Challenge Grant Program. This introduction module is presented by Dr. Peter Ling, who's an associate professor of The Ohio State University. In this introduction module, I will briefly provide some background of the industry. Then I will discuss the motivation behind the learning module development effort. Then we'll discuss the structure of the learning modules, and at the end, I will introduce my colleagues who have made significant contributions in the production of these learning modules. Controlled environment plant production systems regulate microclimate around plants to enhance their growth and development beyond what are possible in open field productions. To achieve this effectively and efficiently, engineering, technology, and science are integrated to provide most efficient plant production systems. Technology level varies among different commercial controlled environment plant production facilities. High tunnel systems typically provide a protective structure without active heating and cooling. Solar is the sole source of light and heat for plant production. High tunnel are typically used for season extension and provide rain protection. Greenhouse systems are equipped with active heating and cooling equipment to maintain temperature set points. More advanced greenhouses can manipulate humidity, CO2, and light levels. Light control equipment include electric light and curtains. Plant factories use 100% artificial light and are highly automated. Some commercial plant factory examples include lettuce production plant factories in Japan and medical vaccine production facilities in US and the Netherlands. There are many potential benefits of producing plants in controlled environments. It uses less resources for the production, it uses less energy, it uses less water, and is more efficient in space utilization, and also cause less environmental impacts. For the energy consumption part, greenhouse tomato consumes about 79% of the energy consumed by field tomatoes. For the water usage efficiency concern, greenhouse tomato requires about 1/2 of the water that's needed by field production. And for the land usage, in controlled environment, seeding propagation area can be separated from the grow out area. That's when the plant is small, their spacing can be significantly reduced. That increases that space utilization efficiency. And plant factories are good examples of vertical production that even further improve the space utilization efficiency. And for the environmental impact reduction, because in the greenhouse environment, the integrated pest management practices can be implemented to preclude insects from coming in and can use beneficials and also can keep sanitation at a high level. That's reduce the needs of the pesticide requirements. With less application and less discharge, the controlled environment can reduce the chemical discharges and waste generation. In addition to use less resources in a controlled environment plant production system, the system also has improved production. It has better yield, it provides year-round production, produce better crop. It can even use marginal land that may not be suitable for open field agriculture production. For better yield, one example is that tomato yield is more than doubled compared to field production. and the crop can be produced year-round in a greenhouse, compared to one example here that is 165 days of field growing days in northern Ohio, which is only 45% of the time compared to a year-round production. And for better quality, the flowering and high control by vernalization, photoperiod temperature manipulation, and plant growth regulator that can provide crops to meet the market demand. For example, the production of poinsettias for Christmas time and Easter lily for Easter, those are good examples. Also, better quality is associated with food safety. The vegetable production in the controlled environment is less subject to outside pathogens. Thus, it can produce higher quality food for consumer safety concerns. Then, using the controlled environment plant production system, we can even produce crop where the soil may not be suitable for plant growth. We can grow plant without local soil. Using artificial growth media or hydroponic system, we can produce plants of good quality on marginal soil. These modules are designed to offer horticultural engineering technology information so that horticulture students will learn engineering skills and engineering students will learn horticultural skills. With a modular design in mind, the learning material can be used independently or in groups for structured academic programs or for continuous education settings for practicing growers. Our intention is to foster a better understanding and better usage of available technologies for efficient production of high-quality, high-yield greenhouse crops. We have developed learning materials under a broad range of subject areas, and there are a number of modules under each subject area. For example, under the introduction subject, we have developed 4 learning modules that include a worldwide perspective of controlled environment plant production, a floriculture greenhouse overview, a vegetable greenhouse overview, and the module you are watching at this time. The other subject areas we have developed learning modules are physics for greenhouse engineering, environmental factors and the effects on plant growth, sample crop production systems and techniques, greenhouse components and system design, sensor and instrumentation, automation and mechanization, greenhouse operation, economics, and greenhouse issues and future technology. As we just mentioned, there are multiple modules under each of the 10 subject areas. Here is another example. Under the subject area of environmental factors and effects on plant growth, there are 5 modules. The 5 modules are light intensity and quality, energy balance, CO2 and gas diffusion, air circulation and boundary layer, and water vapor and vapor pressure deficit. Modules can be used as independent educational units or as components of the course. The modules are designed so that they can be used for both in-class and online learning environments. Each of the modules includes a vocabulary sheet, a presentation, and worksheets. To use the modules, we would recommend a viewer first preview module relevant vocabulary. Then, view the narrated PowerPoint presentations, and finally, complete practice worksheets and review solution key. The team members of this project include Dr. A.J. Both, who is an agriculture engineer of the Rutgers University. Dr. Robin Brownfield, who is an agricultural economist of Rutgers University. Dr. Emily Buck, who is an agricultural communications specialist of The Ohio State University. Mr. Peter Davison, who is a corporate finance consultant of Davison and Company. Dr. Jane Giacomelli, who is a horticulture engineer of the University of Arizona. Dr. Manuel Casira, who is an agriculture engineer of the University of Arizona. Dr. Cherry Kubota, who is a controlled environment plant physiologist of the University of Arizona. Dr. Peter Ling, who is a horticulture engineer of the Ohio State University. And Dr. Margaret McMahon, who is a plant scientist of the Ohio State University. Thank you for viewing this module, and hope you will come back and view other learning modules with us.